Hey everyone, my name's Josh, and I'm here today with Andrew Jackson, who is the author of minigo, which is an open source, unofficial implementation of AlphaGo Zero. So Andrew, thank you very much for coming on the show.
Josh, thanks for having me.
It's great to have you.
I'm having a lot of fun.
Yeah, me too. So to kick things off, could you tell me a little bit about minigo?
So minigo is an open source implementation of AlphaGo Zero that is a ground up rewrite. I'm not affiliated with the DeepMind team. I'm a Go enthusiast who also works for Google, who had the opportunity to write a implementation based on their published papers, and haven't looked back. This was sort of a labor of love for me.
So Andrew, you have an amazing demo of minigo, and I was hoping we could jump right into that and you could explain to me what's on the screen.
Definitely, definitely. So what we're looking at right here is we're looking at minigo playing itself. Right now it is playing both sides of the same game, and it is trying to figure out what the best sequence of moves are for both players. What you're seeing here, if you haven't looked at a game of Go before, is you're looking at these numbered stones that we see here are indicating the order of moves that, that would be played. So you see white 1, then black 2, then white 3, then black 4, and then as white plays the moves, then they switch. So there's black 1, then white 2, switches again. But if you were actually playing a game of Go, it would look like this.
So I notice this board is 9 by 9.
That's right. This is a smaller version of the game of Go, usually used for beginners or people just learning how to play. In this case, it's almost a little bit easier to see everything that's going on, and it definitely will play many games as we sit here and chat, which is also kind of a nice benefit.
Yeah, I can hear your laptop fan whirring away.
Oh yeah, it's cranking out a lot of extra heat for sure. But this is what you would see if you were playing. So I toggled this button over here to make it such that I could play one side or the other. What we see up here in the upper right-hand corner is the graph of who it thinks is going to win. So it thinks this is a very close game. It's swung slightly back and forth, but it thinks that black maybe has a slight edge on this game. As I'm playing white, I could play a move that's, what's the polite way to say this? Not very good.
Yes.
I could play a really bad move. And as I do that, we will see...
A blunder is the word you're looking for.
Blunder, well, you know, let's just say less good. Oh, It hasn't actually completely tanked yet. So let's play another move that's probably not the optimal move in this situation. And we'll see as it should. Yep, There we go. Wow, it doesn't much care for my move.
Yeah.
Black jumps to 95% chance.
Now, is that its confidence it's going to win the entire game?
That's its confidence that black is going to win the game.
Right, so based on that one mistake, you've thrown the game.
Totally. I've basically thrown the game. The value network is rather opinionated at this stage in its training. It has a fairly good idea who's going to win or lose. You may have noticed also that this large mass of white stones has disappeared. There were some other opportunities maybe for white to have created some complications here. I haven't really been looking at the game that closely.
It's really cool.
But my guess is that actually we can scroll back through what it thought was going to happen, and we can look that it thought that what I would play here instead was it thought that I would take those 2 stones on the bottom with 2, black would recapture with 3, and now this is a real game of Go. If you're interested, I definitely learn more about the game of Go. You can check out the rules or tutorials online.
I can imagine sitting down with a couple chess experts and building that value function that tells me how good a board is.
And that's exactly what they did with Deep Blue. That's exactly how IBM built Deep Blue, is they worked with a number of grandmasters to say, how do you evaluate this and why? And they extracted generalized rules, and they used those generalized rules, they just codified them, essentially hard-coded those rules, and used that to guide this exhaustive alpha-beta search or min-max search, where there's a couple of nuances in how that search is performed, but by and large, it always assumes that people take the best move available to them, and tends not to look back, tends not to reevaluate other moves if it's already found what it thinks is the best move. This is very different from how AlphaGo works, which is using something called Monte Carlo tree search. Monte Carlo tree search, there's a little bit of confusion because in the early 2000s there was a breakthrough in Go AI where they did Monte Carlo rollouts, where you would essentially, when you reached the depth of your search, you would very rapidly play the game out to the end 100,000 times. And those Monte Carlo rollouts would be used to ascribe the value of the position. So if I very rapidly fill up the game, like 2 complete novices were playing, just randomly picking legal moves, and one side wins slightly more than the other side, then I could guess that this is a good approximation of the value. Go is a game of perfect information, just like chess. So there is, in theory, a perfect set of moves that could be followed, such that the person who plays first could always win. Just like tic-tac-toe or Connect 4, it is a game of perfect information. In practice, though, there are so many possible permutations that it is not feasible to explore all of them.
There's probably more possible Go games
That's
when
right.
there are atoms in the
That
universe.
is that's a thing that has been said before.
Yeah.
We can roll back. This is how the game starts. Is it thinks that this 12-move sequence is what's going to happen. But if we go 12 moves in, we can see that that isn't actually the sequence that occurs. While it's trying to look as far into the future as it can, when the future actually arrives, it may be a little bit different than we intended, which is getting a little metaphysical for what is otherwise a fairly concrete task here. But hey, let's go.
So I see multiple
ahead.
windows on the screen.
That's right.
So what are the 3 small boards?
Right. So what we're looking at, I'm going to go ahead and right now white is going to resign, and it's going to start another one here, as it realized that black is basically a sure thing to win this game. What we're looking at is we are looking at on the main board we saw the principal variation, which we were talking about, white 1, black 2, et cetera, et cetera. What we see in the upper right hand or the uppermost board is each of the leaves of the search prior to being evaluated by the neural network underneath minigo. The middle board is a heat map of the visits. So the darker squares are being explored more often. So this is a quick way to see which moves it's considering. And then the bottommost board is one of the stranger views of the game. That is the change in the value of the board based on where they play. So for instance, when it's black's turn, if black doesn't play at this point in the middle, changed, the whole board will suddenly look better for white. Whereas when it's white's turn, if it doesn't play a critical point, the rest of the board suddenly becomes very good for black.
It's also cool, it has this heat map showing which moves are likely to be good. So does it always explore the best moves, or does it explore the space in a different way?
No, the idea behind Monte Carlo tree search is to balance exploration and exploitation in a way that doesn't lock it into a single path in a way that an alpha-beta search might, or the way that chess engines have historically searched board positions.
So I know minigo is powered by a CNN, or a
Right.
convolutional neural network.
Right.
And I know these are similar to the CNNs we would use to classify images, say
That's
of
right.
cats and dogs.
Right. So it's a residual network similar to ResNet or whatever your preferred example is, which has a number of shared layers of convolutional layers with your standard ReLU, what do you want to call those? Thresholds, activations. Your standard ReLU activations, followed by another convolutional layer, and then the skip connection. There's a whole stack of these shared layers, which at the bottom of that stack, or at the top, I don't know which orientation.
Depends how you orient it, yeah.
Right. It fans out into a policy head, which gives it a heat map of the most likely moves to be played, and a value head, which just spits out a single number indicating who it thinks is going to win. That's a little bit different than what we see in the upper right-hand corner. This is actually the average of that value number over all of its searches. So this is not just the output of the value head. That's the average of all of its searching. So it's a little bit different, but it's ultimately made up of those outputs of that value head. Similarly, the policy N diverges from the original estimate of the policy heat map based on the results of its search. So the policy heat map says, well, start looking here, but the value network may say, okay, that thing that we thought was a really good move actually doesn't work at all. Let's look at that much less. So this actually is a really nice segue into how minigo learns, which is it's entirely reinforcement driven, reinforcement learning driven, right?
Yeah.
Where this heat map N forms the target for the next version of the policy head. So the loss function that we're trying to minimize here is the difference between the policy output and this visit heat map. And the
I'm just thinking. That's
right, you got to think about it.
Yeah.
So the loss function is the difference between the policy heat map and the actual visit counts after search, and the sum of that error, the cross entropy error there, and the mean squared error between the value estimate and the actual result of the game. So each of the input examples to training is the policy output, the original policy output, the policy output revised by search, the value output, and the actual outcome of the game. So the difference between the moves that we started looking at and the moves we ended up looking at the most shapes the policy network towards the moves that search thought were best in this situation, and the value loss shapes the value network towards predicting better in the future, basically.
It's really cool. So Andrew, it's been great chatting with you. Thank you very much for coming on the show. Thanks everyone for watching. You can check out minigo at github.com/tensorflow/minigo, and you can learn more about how it works and Go itself using the resources that Andrew mentioned. So thanks very much, and we'll see you guys next time.
Send me pull requests.